We're pretty lucky in biology because we don't have to study every single element. So, of the 96 naturally occurring elements, these in this table are the most important. 96.3% of us, and also about the same in other living things, is oxygen, carbon, hydrogen, and nitrogen. So over here, oxygen, carbon, nitrogen, and hydrogen. Hydrogen has an atomic number of 1, carbon 6, 7 for nitrogen, and 8 for oxygen. So these first 4 are very early in the periodic table, and we know their name, we know their atomic symbol now, and also you know their atomic number. And the atomic number, again, is the number of protons. So these 4 elements and atoms of these 4 elements make up most of the elements in the molecules that make up our cells and our tissues and our larger structures. Then there are other elements that make up a very small percentage of our molecules: calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. We find the atoms of these elements connected to molecules that mostly contain the 4 big types of elements. There are also trace elements, and these are required in tiny amounts. Zinc and iron, these 2 are cofactors, so helpers of enzymes. Enzymes are catalytic proteins in our body, and so most of these things are actually helpers of enzymes and proteins in cells. We don't need them in very high quantities, but these in this table, the tabled elements, are the most commonly found. So now within each of these elements are atoms. An atom has a specific structure. In the core, or the nucleus of the atom, there are protons and neutrons. So these subatomic particles make up the nucleus of an atom. Protons have a positive charge, and neutrons don't have any charge at all, so the neutrons are neutral. Outside of the nucleus, there are electrons. Electrons are our 3rd type of subatomic particle. And the electrons can always be found kind of whipping around, circulating around the nucleus of the atom. Here they're shown in a fixed position, but they're usually found kind of within a cloud, within a defined distance from the nucleus of the atom. And every subatomic particle is found within the structure of the atom. The subatomic particle numbers will mostly be the same for an atom of any kind of element, although we'll see some variance in neutrons. And every element has a specific number of subatomic particles. So let's go back to the periodic table and the elements and think about how we can determine how many subatomic particles are found within each atom. The atomic number is the number of protons found in an atom of a given element. So silicone here, which is not one of those that we find in us, but silicone has an atomic number of 14. So in an atom of silicone, the nucleus of the atom has 14 protons. Now, the mass number, or the atomic mass, or the atomic weight, is the number of protons plus neutrons found in an atom of a given element. And for most elements, the most common type of atom has the exact same number of neutrons as it does protons. So what that means then is that the atomic weight here should be 28. And this measurement is in atomic mass units. Every proton and every neutron weighs 1 atomic mass unit. So 14 protons plus 14 neutrons would give us 28. But the atomic weight differs here because in most elements there are isotopes or alternative forms of atoms that differ in the number of neutrons. The atomic number, the number of protons, never changes, but the mass number can vary based on the number of neutrons found in an atom of the element. Now for silicon, most of the atoms have 14 neutrons, and so most of them have an atomic weight of 28 atomic mass units. But there are some atoms out there of silicon that have a greater number of neutrons, and so the average atomic weight is a little bit heavier than 28. Isotopes are the atoms with the same number of protons, but differing numbers of neutrons. Isotopes are different forms of a single element. So for example, carbon. 99% of carbon atoms have 6 protons and 6 neutrons. But there are 2 isotopes of carbon out there, carbon-13 and carbon-14, that differ in their numbers of neutrons. So the number of neutrons that are found within the element is 1 or 2 more than most of the atoms of that element. An isotope has a different number of neutrons from the standard number, and some of these isotopes are radioactive. They spontaneously decay to release energy. They can decay to atoms of the same element, or they can actually decay to a different element. But I like to point them out here because in the medical field, there are many useful applications of radioactive isotopes. So, for example, technetium is a radioactive molybdenum element, and molybdenum decays into technetium. And technetium can be combined with some sort of delivery molecule that targets specific organs. This can be injected into a patient. It has a very short half-life, so it doesn't cause damage to tissues. And the half-life means that it decays very quickly. A short half-life means it decays quickly. And so here is, for example, a bone scan where specific types of cells were targeted so that different tissues could be highlighted. This is the delivery molecule connected to technetium. Okay, now also outside of the the nuclei of atoms are electrons. An atom of hydrogen has 1 proton, and usually the atom of an element has also the same number of electrons. So it's kind of easy. Number of protons equals number of neutrons equals number of electrons. Now the atomic weight does not take into account electrons because electrons have like negligible weight. So the atomic weight only takes into account protons and neutrons. But there are these electrons circulating outside of the nucleus of an atom. An atom of carbon has its 6 protons because its atomic number is 6, and it also has 6 neutrons in here, but it also has 6 electrons. And the electrons are a defined space away from the nucleus of the atom, and those spaces, actually there's more than one space, more than one shell, those spaces are filled with a specific number of electrons and in a specific arrangement within those shells. So for example, the first shell outside of the nucleus of an atom holds 2 electrons, and they tend to pair up. So what we do is we show the first 2 electrons associated with the atom in the first shell and as a pair. Now, an atom of carbon has 6 electrons. So the next 4 can fit in the next shell, which can hold a maximum of 8. Those 8 like to form pairs with each other, but first they fill up 4 spots within the shell. And here we have atoms of elements that have a greater atomic number. And so, for example, nitrogen has 1, 2, 4 electrons in the outermost shell, but because there are 7 electrons, we need to assign a spot to one more, and so we give it a partner. 8 electrons, we have 1 pair and 2 pairs. But notice that we have 2 unpaired electrons in this outermost shell. And atoms are stable when their outermost shell is filled. So in this state, which is the state of the electrons in an atom of oxygen, it's not most stable because we've filled up all the electrons in the outermost shell and we've given all the electrons that we can partners. But what an atom likes to have is its outermost shell filled with all pairs of electrons. So you can see phosphorus with its 15 electrons. 2 fill up the innermost shell, 8 in the next shell. Then the next shell to be filled with larger atoms, elements with a greater number of subatomic particles. The next shell holds 8, and they all hold 8 after the first. We've assigned 1, 2, 3, 4, and then 5 electrons in the outermost shell of phosphorus. So what we have is something called a valency, or what we have in the outermost shell are the valence electrons. These electrons are unstable. We call the entire group the valence electrons, but the valency is the number of electrons that need to find a partner. The valency here is 3. Valency of an element or an atom of an element is the number of bonds it is able to form around it. The valence electrons are those that take part in chemical bond formation. So while these are the valence electrons in the valence shell, only these electrons out of all the electrons can actually participate in chemical bonds, and they'll do that in order to stabilize the atom. The valency number explains the formation and the number of bonds that are formed between atoms. These electrons, the valence electrons, are related to how the atoms interact with other atoms. So what we're going to look at next is how atoms of 2 different elements join together to form compounds or molecules. Sodium is a metal, chlorine is a gas, but when we put together atoms of sodium and chlorine, we get sodium chloride, which is table salt. So properties of the individual elements are going to be different than properties of the molecules or compounds that make up those elements.